This is the lab. So the lab was to basically come up with a way to do this kind of behavior where we generate a random character. So let's go problem by problem. So first thing we're going to do is start off with a blank file. Ignore this. Set a new file. Okay, and before I do anything, I'm going to make sure that this compiles and runs. No errors. Cool, ran with no errors. All right, first thing we're going to do is create a function called print divider. And this one I asked you to print out 51 stars in a row. 2 rows worth. So the way you print out 51 stars, or 51 stars, is you write a loop. And all this thing's going to do is just going to print out an asterisk. And for brevity, this. So this will print out 51 asterisks. And I'm just going to call it once for now. Just to prove, again, I'm not doing anything. I just want to prove that I can print out 51 of these. And if you guys can see, there's 51 stars. Okay. So I want to do this twice. I want to print out 2 rows worth. So one way I could do this, I could copy and paste this twice, which this is okay. If you really want to do it twice, though, you can write another loop that's outside of it. So you can make a nested loop. And just do that twice. So every time you call this, it'll print it twice. So now I should have 2 rows worth. There's 2 rows of stars. Let me close my, I'm going to show you guys this later. And what I wanted to do was just see out like that. And then print out the divider in between, print out the name in between that string. So you basically get a header and asterisks. Okay, that's prepare to program edition. Cool. So this function is just a void function, takes no arguments, and literally all it does every time is print out 2 rows of asterisks every time you call it. I'm going to do this too. I'm also going to do int dummy. And it's just going to print out 2 rows of asterisks at the top, and then I'm going to call it again to print out 2 rows of asterisks on the bottom. Next thing I asked was to create a function called print stars that takes a single argument with the number of stars you want to print. So print stars. It's going to take an integer. What did I ask for? Number of stars. Like that. There's my prototype. And the way I usually work is I copy the prototype, and I'll scroll down the bottom, I'll paste that prototype, and I'll delete the semicolon, and I'll add that. And all I'm going to do is literally just this. Instead of 51 here, it's going to be number of stars. So that's all that function is. Literally, I just copied what this was doing and put it down here and replaced it with the argument instead of hard coding it to be 51. Now I can do print stars 30. I'm going to prove that it works. There's 30 stars. I can also do 300 stars. So this function will now let me print any number of stars that I want. Cool. So it's going to be 30. I'm going to do it twice, because this is where we're going to do our names. Next is going to be a function called roll d6 that returns an integer. So this one has no arguments and it returns an integer type. So I'm going to scroll down to the bottom. And what we're going to do is we need to return rand modulo 6 plus 1. In order to have this rand function, though, we need a couple things. We need stdlib. We also need time, so that at the top of our function, we can do srand. There we seed our randomizer. And now this roll d6 is literally just this line here, which just returns me d6. So I can see out that. I'm going to do it a couple of times. So 4, 3, 5, 3, those look like random numbers to me. Each one of those is a random number. So I've proven that that works. Cool. Next one's going to be roll die, which takes a single argument for how many sides I want to roll. It's going to be exactly the same as this, except instead of no arguments, it's going to take a single argument with a number of sides. I'm going to go all the way to the bottom. And this is going to be, again, exactly the same as roll d6, except instead of 6 sides every time, it's just going to be number of sides every time. Now I can roll a 100-sided die. Oops. I can roll a 100-sided die. Maybe I'll roll 4 of these. And let's just do C out. Let's print out 100 numbers, or 4 numbers, 22, 71, and 93, and 74. All right. Okay. So that's our roll die. Next is our random number and range function. So this one's going to be return an integer. It's going to take 2 arguments, a min and a max. Again, I'm going to copy this whole line, go all the way to the bottom, like that. And this, I'm just going to return a dice that I roll between max and min. So this is going to be the range of numbers. So if this was 75 and this was 100, this is going to roll me a dice between 75 and 100, which is a 25-sided dice. I'm just going to add min to it. This adding min will make sure that my number is at least this amount. So if I were to substitute numbers in here, 75 on 100 would give me this formula. And I can just replace this 100 minus 75 with 25. So I'm basically rolling a 25-sided die, and I'm always adding 75 to it. All right. That's my random number and range. I'm going to write another function called print stat, which takes 2 arguments. It's a void function. It's going to take a string. So I'm going to do pound include string here. Let's move this up to the top. String name, int value. Copy this whole line, go all the way to the bottom, remove the semicolon. And all this is going to do, I actually gave you the code you can copy here. Set W, just going to do that. And in order to use the set width, you need to do one more IO minute. And this function, all it does is just prints out the name colon the value with extra padding assigned with it. And I wanted you to call it 3 times up here. So in between printing stars, I'm going to print the stat for strength. And for the value, I'm just going to get a random number in range between 20 and 60. I'm going to do this 3 times, 1 for dexterity, 1 for intelligence. And maybe we could do different numbers here, 40, 10, 30. And now that this function is written, every time I run it, I get these 3 stats, strength, dexterity, and intelligence. But my random number is not 10, it's max minus min here. Min. So there's my strength values. Okay, so there's print stat. Now we're going to write a function called random name, which returns a string. This thing returns a string called random name, takes no arguments. Okay, copy the whole line, go all the way to the bottom. I'm hitting Control End here to go all the way to the bottom. And this thing here, I want to get a string result. It's going to start off with nothing. The name is going to be blank. I'm going to return the result at the end. So in between this is where I'm going to write my code. Get my name length. It's going to be equal to random number in range. I'm going to get between 6 to 16 characters. And for that name length, I'm going to take my result. I'm going to add a character onto it. So if I do this, it will add the letter A onto that result however many times I want. But instead of just typing in the letter here, what we can do is get another random number in range. And this random number in range is not magic. It just happens to be the codes, the ASCII codes for the capital letters between A and Z. Now what I can do is I can print out, I can do cout, random name, at the top, right before I do my strength. And there's my random name. Happens to be a square bracket there. Make sure I got the random number range between 65 and, did I do that right? Maybe I want this to be 90 in my case. Bun with texters, my name. You can also format this as well. You can just do set W 15. That way it'll be formatted like everything else. Maybe I do name here. That way everything's nicely aligned. I do 15. What is my set width here? 15. Okay. So there's my print name. Finally, I want to do the random class. So what I wanted you to do was create an array of classes. And this is going to be equal to, I'm going to initialize it right here. I'm going to do warrior, mage, cleric, Templar, and pyromancer. This is going to have 5 elements in it, 5 classes total. I'm going to write a new function called string random class. Copy this whole line, go all the way to the bottom. And all this is going to do is going to return me from classes. I'm just going to roll random number in range between 0 and 5. And that way, when I print out the class, I can get Templar or Mage. Okay. So that's how I get the random class. My function is just return me out of my classes array a random number in this range. So with all that combined, I can take all of this and now move that into a new function I called create class. So I'm going to make a final function called create character. Sorry. Copy this whole line, go all the way to the bottom. And what I'm going to do is I'm actually just going to move. I'm going to take all of this stuff. I'm going to cut it out of here. I'm going to paste it all down here. So now I have a function that does all this. And I'll call this function 100 times. And in here in main, I'm going to write a loop that goes 100 times and call create character. So each one of these characters is different. There's a cleric, mage. Every single one of these has, some of them have no classes. That's something I'll have to fix.
You rolled to 5.
Oh, because I rolled up to 5. I want to roll to 4. So these are great. I have something I can create a class, but my names are kind of crappy. I don't really like most of these names because they're just literally random letters put together. Let's do a little better. So what you can do as an example, just like how we do classes, we can make name prefixes. I'm going to create 5 of them. I'm going to have you guys shout out some name prefixes. We can do name segments, create 5 of these. And we can create name suffix, create 5 of these. So what we can do is we can put kind of pre-generated random bits of names in here. These can all be capitalized, like, I don't know, Va is one. You know, Pel is another. Trot. I don't know. Maybe I'll have like, what are other characters? Red. And give me another one. Soul. Those are 5 name prefixes that I can do. What about segments? These can be a little bit longer. Meander. Logar. Potter. Kachu. And then we'll do Lucy. These are in the middle. How about things that like Bob? And these will be the finishers. So Sar, Izard, Hurdle. Give me some more. B. Anyone have another? Ash. Ketchum. So now I have these 5 pieces. So the best part about it is that I can go into my random name function here. I can just delete all this. And what I can do is I can just take name prefix. I can get a index into a random number and range between 0 and 4. I can add the name segment. And then I can add the name suffix. So I'm basically taking one piece from each of these arrays and I'm combining them all together to get the random name. It's 100 characters. Pelogar Ketchum, Trot Bob Ketchum, Solkat Shurl, Red Potter Erdle, Pel Potter Izzard. These names are silly, but like Trot Lagar Izzard, that's a good one. Soul Bob V. So you can see like the names are a little bit more reasonable. If you had like way more prefixes and segments and suffixes, you can make a lot better names. The last part of it is how would we use a generative random weapon for each of these? Same idea. So we could make another string of weapon prefix, maybe another string of 5 of these. And maybe I can make some of these be like fiery, quick, rusted, maybe nothing, godly. However many you want to make. And then you can make another array of weapon types. Maybe dagger, bow, broadsword, stick, pillow. We can make another string, which is suffix, of the whale, of the zodiac. I don't know. What other ones? Of harming,
The legend.
of softness. So we can write another function that's create me a random weapon. Copy the whole line, go all the way to the bottom. And all this thing's going to do, I'm going to actually copy this whole thing for a random name because I see a lot of stuff I can reuse. Rename name to be weapon prefix. Weapons. And then weapon suffix. Okay. And at the very top here, under if I go to create character, there's my create character function. Right below class, I can also type a weapon. And now all 100 of my characters are going to get a random weapon too. Quick broadsword of softness, godly stick of the zodiac, godly pillow of harming. Looks like I need to put some spaces in between there. Rusted stick of the zodiac, godly stick of stickiness. Yeah, quick stick of softness. So you guys get the idea. So we can add more and more properties and more things that get printed out for our character. All right. So let me do this. I'm going to, what I'm going to do is I'm going to put this up on Zool so you guys can grab it and modify it. I'll put this up on Zool. I'll call it character gen. So you guys can run it and see how this works and see how different yours was from mine. Okay, any questions? All right. So I want to spend the last hour doing lecture. We're going to start our discussion of pointers on page 144 in the C++ primary book. And I'm going to use a brand new file as an example to kind of instruct some of this. So C++ so far has been one file. Variable types are very simple. A lot of C++ development though comes from the usage of one of the types it has called pointers. So there's kind of two ways to run a C++ program. One is to use what's called static memory, and the other is to use what's called dynamic memory. And so the difference here, I'm going to kind of explain in the context of like taking a vacation. So let's say you were to plan a vacation to go to Hawaii. So one way you could do that vacation is you could plan everything ahead of time, having a complete agenda, and once you get to Hawaii, no matter what, you follow that plan, even if it's raining or one of the islands sinks under the ocean. You literally follow the plan. That is akin to what static C++ is. So when you're using static memory in C++, you basically stick to a plan and you never change it. You're always going down that plan. C++ is a really powerful way, though, of allowing you to do things dynamically. So the other way you could take a vacation to Hawaii is just say, hey, I want to go to Hawaii. And when you get there, you kind of decide what you want to do at the time you get there. Maybe you decide you want to go eat some food trucks, or you want to go drive to some islands. Your plan is not locked down to what you decided ahead of time, which means that you are flexible and you can do whatever you need to when you get there. So C++ lets you do that too. So what that means is when you are making something like a game, sometimes you don't know everything that you need ahead of time, especially when it comes to games that are like big open world spanning games. For instance, one of the reasons why you need to use this is let's say you just type in a character name, right? Some people, let's say there's no limit to the character name. Sometimes you want to have a character that has, 100 characters in a name. You might not know that at the time that you wrote your game, but you can write your program in such a way that you don't care if you know that or not. You could actually write your program so you'll get whatever space you need to when you need it. Same with, say, inventory. Let's say there's a game out there that has unlimited inventory space, right? So you have as many inventory items as you want, unless you're playing like a Minecraft, right? You guys ever play Minecraft? Nope. No? No one of you have never?
No.
Never.
Yes.
I'm not interested in it.
No? What about, Minecraft's pretty cool. What about, I guess Skyrim is another good example?
Of course.
So you know how in the house you can just toss whatever like crap you find? Just throw like all your cheese wheels and your books and your like candlesticks that you steal all into your house. How do they write it in such a way that they know how to save all that information, how to store all that information? They don't necessarily know how many items you're going to have in your house at one time. So what they do is they write the game in such a way that they can dynamically increase or decrease whatever they need to use when they discover they need to use it. And that's what pointers do. So pointers are basically the way that you can allocate dynamically whatever you need to at the time that you need to. So we're going to get into more of that stuff kind of probably next class, but I kind of want to give you guys an idea of why we're using pointers. Because if we didn't use pointers, what we'd end up having is a game that's very static. It doesn't have any idea. It cannot be flexible, which is probably fine for a game like Pong. We don't have like changing elements, but if you ever have a game like Skyrim or Minecraft or anything that has dynamically changing things, you want to be able to use pointers to leverage that. That's why pointers are very important. So even the things like Overwatch, like we use pointers for things like how many players are on your team, right? It's right now we try to limit it to 6, but in theory you could have up to, I don't know, 100 players on a team, but we don't know that at the time that we're getting into the game. In fact, some of our games only have 1 player versus another player. Also, like bullets. How do we keep track of how many bullets have been fired? How do we know, like, how many decals you draw on the wall? Like, every time you shoot the wall and you leave behind little bullet marks, you don't know how many bullet marks you need to keep track of. That's something dynamic that we figure out while the game is running. And because it's dynamic, we need to use pointers because pointers are the only way to basically get access to this way of dynamically allocating memory. All right. So that's why we're going to use pointers.
I have a question. For something like that, would that be more on the computer graphics programmer side? Do you keep track of something like that?
Decals are definitely more of an engine thing. If you're talking about bullet holes and bullet
Yeah.
marks and stuff, that's more of an engine programmer thing. Yeah, a rendering engineer would probably do some of that stuff too, to make it look nice as well as to make it perform so it runs at 60 FPS on a crappy laptop. Like, or these crappy computers. It's not bad. I'm just kidding. But these computers here, like getting it to run 60 FPS on these computers. So I need to talk about pointers though. I need to talk about memory, and to talk about memory, I need to talk about addresses in memory. So I'm going to take a little bit of tangent here to talk a little bit about how computer memory is organized. So let me. I wish it's the best way for me to record this for later use. Let's do this. I hope these computers have Excel. Hey, they do. All right. So you guys have been playing games probably a lot. You might have been using computers for a lot. Do you ever think about how a computer works, like with regards to how your RAM works, or like
Yes.
how it knows? Have you guys ever taken classes to understand how stuff is stored? Yeah. Do you know why like you need more RAM sometimes, or why you like run out of memory?
It
Or,
goes.
like-
It goes by the task that you have, the amount of tasks that's required.
Yeah, so however much memory it needs, it tries to get. Some programs need more memory than others. Some programs are more memory. Like Chrome takes up a huge amount of memory. But like, memory is a finite resource on your computer. You don't have unlimited memory. If you tried to open, like, you couldn't open every single program in the world on your computer all at once. You'd eventually run out of memory, right? Like, that actually is because the computer has to have a place to put everything that it wants to store. So here, I'm going to represent memory. This is going to be our RAM. You can imagine that I'm going to these 2 columns here. Going to be our memory. Stuff. So this is going to represent computer memory. We have, this is basically all it is. It's just 2 columns. This is how RAM is. You have where you want to store it and what you have in there. This basically, imagine I have, this is Excel spreadsheet represents a stick of RAM that I have. Now these memory addresses, RAM, every single place you want to store something has a unique address associated with it. So I'm just going to give these numbers. I'm going to make these things all very big. Okay. I'm just going to copy this all the way down. I'm going to start at 100 and go down to 1001. I'm just going to copy this all the way down. Okay, so they're all increasing in number, right? So this is basically how RAM is. You have to tell it where do you want to put your stuff in computer. Every time I start up a game, the first thing it tries to do is say, hey, I need to start putting stuff somewhere. Like you start up Call of Duty, you start up Skyrim, the first thing it needs to do is like, well, shit, I need to run this program. Hey, Windows, give me a place to put some stuff. Windows is like, okay, start here. This is where you can start putting some stuff. I have some room here. No one else is using this right now. Go ahead and put your stuff here. Okay, cool. Call of Duty's like, all right, well, I'm going to start putting stuff here. I need more memory. I need even more stuff than this. It starts filling in stuff here. with data that it needs to actually run the program. This stuff here, all of it's kind of zeros and ones. So all of it just looks like numbers to people that are looking at it. The important bit is that sometimes the stuff takes up like just 4 of these rows. In this case here, this right here is the bare minimum you need to represent an integer. You need 4 of these pieces to represent a single number in memory. Each of these things represents a single byte of memory. I'm going to use these in memory addresses as if they're bytes. I need 4 of these to represent a number. Why do I need 4 of these? Why can't I just use 1? Well, what happens if I just use 1? Okay. If each of these things, if each of these places in memory can store a single byte that is 8 bits, so this thing can store a maximum of something that looks like this. That's the. Oh, I actually want it to show.
Use hexagon.
Don't mind the X in front of it. This is the highest. This is the most amount of stuff it can store. For example, the only thing it can store in here would be a number like this, like that. Each of these things is the stuff that it stores. I'm just going to use this. There's an example of one of the things it can put inside there. That is the most it can represent in one piece of memory. That is the smallest little bit. That is called 1 byte of memory. That is a number, actually. If I were to put that in a calculator, I'm going to take this, and I'm going to put this in binary in the calculator, and that is the number 171. What is the highest number I can represent in here with all? That is the highest number I can represent in a single piece of memory. That is a limit. It's been that way since the beginning of time, and it will be that way until the end of time, probably, as long as computers are around, maybe until quantum computers are around. What is that number? Happens to be 255. So that is the highest number that a single piece of memory can represent. That number is not nearly big enough to represent all the things that we need to, which is why sometimes we need more than just 1 row.
Why is it like that, though?
Why is it 8 bytes per
Yeah.
bit? 8 bytes. I'm sorry. Why is it? It's 8 bits to a byte because that's how many that's how this memory is actually organized.
Why is it like the end of time? Like, why?
Because we can't physically the way we physically make chips is we have a single transistors, like the tiny little bits of electronics that live inside RAM, is built to support storing one of these things. You have billions of these in a stick of RAM, right? And every single one of those transistors functions the same way, where it stores a single piece of memory like this. Probably before the modern computers, it might have only been able to store like one thing like that, either a 0 or 1 inside of here. So, but now with the way that all our memory is being organized and the way that it has to be compatible with all of our operating systems, everything's revolving around the idea of storing 8 digits right here. But 8 digits is not enough to represent, that can only represent the number 255 total. So if I combine these two, if I were to say, okay, well I want to represent a number with 2 of these, imagine I just put 2 of these back to back to one another. Imagine it was one long number instead of 2 of these like this. Imagine instead of these 2, I could just stick these end to end, right? Imagine I was able to just combine these 2. Then what is the biggest number I can represent with 1, 2, 3, 4, 5, 6, 7, 8, 16 ones? So there's 1, 2, 3, 4, 5, 6, 7, 8. That's 255. What if I stick another 8 numbers on there? 1, 2, 3, 4, 5, 6, 7, 8. How big is that number I can represent? 65,535. Okay, it's a lot bigger. It's exponentially bigger, right? What if I stuck 4 of these numbers together? Like I said, you need 4 of these to represent an integer. How many numbers do you think that represents? I'm actually going to type these out. I'm going to do 32 of these. 5, 6, 7, 8. 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. Oh, I can't even do that many. We're going to do 2 at once. I will tell you what they are. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's 32 ones. That's the biggest number that 4 of these pieces can represent. 4.2 million. Okay, that's a lot better. That's usually high enough to represent things in games, typically, I mean, for like values, but also it's big enough for things that we want to work with for like storing things like, oh, I want to store how long a name can be. These numbers here also can represent letters. They also can represent abstract ideas like a bool. For instance, if I want to store whether something is true or false, maybe this thing represents a single integer, a number. What about this? What about these next four? What if I want to represent true or false? Literally, it's just 0 or 1 here. Bools are usually represented by one of these, 1 byte for a bool. A character is also this way. If I want to represent a character, like the letter A, if I type the letter A there, it's actually represented by the number 65 in there. That's why it only takes up one piece here. So a double, you guys have used doubles, takes up 8 of these total. Okay? A double takes up 8 pieces of memory here. This is for one variable, it takes up this much memory. Okay? One variable. But that double can represent very, very large numbers because of how many bits it has to work. Okay? So a double represents that many. So if I ask you, if I have a double, I'm just going to make a variable called x equals 42. I'm going to make this thing giant. There's my variable. This is all part of the same thing. Oops. This is all one variable. This is my variable here. So that one variable that I just declared basically looks kind of like, not exactly, but it might be 0. That's what it represents. You can kind of think of it like that. I have a variable called double. It takes up that much room and represent that number like that. But each of these, I didn't talk about addresses here yet. That variable has an address. That's where that variable starts. Okay? This variable x starts at memory address 1000. The number associated with it is 42. Why don't I make another variable called int y equals 10? Remember, variables for y are this will be 10 here. Okay. So now I have two variables in my program. This is literally, I just wrote a program that declares a double x and int y. This is how my memory is starting to get laid out. I did 9 here. That's actually my mistake. Actually. Move this up. There's my variable. So the address is really important because we're about to show you how to get that address. So the address of the variable x is 1000. The memory address of the variable y is 1008. That's where that variable data lives. That's where that number 10 starts. If I were to type in the number 300, remember, this thing can only represent 255 at the most. This thing would essentially be equal to what 45 is, whatever's left over. It's not exactly, it's all in binary, so it's not quite represented like this. It's whatever 300 is. Okay, 300. 1, 2, 3, 4, 1, 2, 3, 4. So this is 1. That's what this is in binary. That number 300 is stored in 2 values. It needs to carry over. That memory address of y is at 1008. These are what we're going to be working with today for C++. We are going to be working with finding out how C++ puts variables into memory. Because this column for memory addresses goes for however many gigs of memory you have. How many of these do you think there are for like 8 gigs of memory? If each one of these things is a byte, and I have 8 gigs of memory, there are 8,192 megabytes, that many kilobytes, and that many bytes. So 8,589,000,000 rows of this. If I were to make this Excel spreadsheet 8 trillion rows, that would represent every piece of bytes in an 8 gigabyte stick of RAM. Okay? And that would represent the space in which we're working with for memory. Okay? All right, do you guys get the general idea of how the memory addresses are working? Like everything that we store has both a place and what's in that place? Okay, I want to show you guys this in practice. I want to show you guys this working in C++. Okay, so I'm going to write a very simple program. It's not even going to do anything. I'm going to create 2 integer variables called donuts. That's all I'm going to do. Maybe I'll see out. Okay. My program is literally just going to print out what donuts and cups is. It should be 10 and 4. You see 10 and 4? Okay. So let's see what happens when we start investigating the memory of these things. So there's a new operator I want to show you guys. So far we can print out donuts and cups. What you can also do is print out where that variable lives in memory. So if I wanted to, I could do this. Donuts memory address. If you put an ampersand in front of the variable name like this, that will get you the memory address of where that variable is. This memory address for where that variable is. And even though this variable takes up 4, it will only return you where memory starts. So if I were to print out the address here, it's not actually going to start at 1,000. That was just my contrived example, but it will start at some point in memory. And I'm going to do the same thing for cups. I'm just going to print out the memory address of cups. So donuts 10 is at this memory address, 35FA98. Yeah, that's a hex address. 35FA8C is where cups is. So that's interesting and everything, but like, how do I actually see that? So I want to introduce you guys to something called the memory debugger. And you probably aren't going to use this in this class too much, but it is something really important to know. So let me show you. There's a window for memory. I'm going to pull this guy out. This is the memory of our program where it's running right now. So if we go here, and I'm actually going to look at the output, 35FE68. I'm going to type that up here, 35FE68, 0x0. So 35FE68, these 4 right here, the things I've highlighted, which are super tiny, which I wish you guys could read, this is my donuts variable. And it's represented the numbers like this. There are 4 bytes. Each one of these pairs of numbers here represents a single byte of data, represents up to 255 numbers. And you see here, 0A is the number here. If I do 0A, that's a hexadecimal number, and I put that into here, 0A, and I convert that to decimal, equals 10. If I take the address of cups here, 35FE5C, I have 4 bytes here. And look, the first number is a 4, because that's what cups is. But check this out. See, watch that 4 up there. I can actually change that to be 12. Or I can change that to be 1. You guys see that number changing? 2. It's turning red. It's like super tiny. I'm going to turn on the magnifier for you people that can't see. You guys see that number, 3? Up there? This guy right there? So I'm going to go down here, and I'm going to change. going to change this to 4. It's 4. But see, it takes up 4 bytes. So what happens if I put in a really big number? Let's put in a number, I don't know, 9,001.
Yay.
Look, it's taking up 2 bytes now. Because it needs those two. So remember I said that if it's over 255, it needs more space. So if I go even higher than that, like 90,001, now it's 90,001. Now it needs 3 bytes. And this is hex here. Okay. If I try to go too high, I just typed in a number that was way too high, and it rolled around and said, well, shit, I don't know what to do. This is the best I can do. It still takes up 4 bytes. Okay? You can see here C over on the right. That's uninitialized. It doesn't have data for it. That's uninitialized memory. And here's our memory for our donuts variable. So there's, see how it says 0A? I'm going to change donuts to be, I don't know, 2,000. So there's donuts changing right there in memory. Okay? This is actually what's changing here.
What's the stuff on the side?
This stuff here?
Yeah.
This is the ASCII representation of the number that you typed in. Sometimes you get reusable stuff here, sometimes you don't. Let me show you an example of where that's actually useful. If I make a string, foobar, I don't know, I'm just making crap up. So I'm going to run this again. This time I have a string here for Dark Souls 3. And I'm going to get the address of foobar. I could do that down here. If I just do this. I can go to this memory address. I don't actually know if this is going to get me what I need. Sorry, give me a second while I find this. There we go. So do you see here on the right side now? Do you see how it says Dark Souls 3 is not a good game, question mark? That's actually what it thinks is there in memory, right? So that is actually, you can see, do you see all the rest of this stuff? All the rest of this stuff on the right? That's all kind of the rest of the program. You can actually read some stuff here, like C users, AIOC, user profile, this is all the executable data here. Visual Studio version 14. This is basically our entire program that we have running right now in memory. You can see what's in there.
Is there anybody that can read the ASCII?
It's not really, this is not really meant to be like a legible thing. Typically what you do is you look at this here, the values on the left, because these are more useful most of the time because they represent like the data that actually is in there. This is only useful if you actually want to see it as ASCII. There's a way you can actually show you, you can change the display here to be Unicode text. So you can get some characters, if it is in Unicode, you can see it's starting to do Chinese characters. Or you can just do no text at all, and that's fine too. This stuff on the right is not as useful as the stuff on the left. So that's how memory works, right? So now we have a way to get memory by printing out the ampersand of things. Okay. You guys have questions on the memory stuff so far? We haven't even gotten to pointers yet. We're just doing the memory stuff because memory is just as important. All right. So if I were to change donuts to be a double, and then I look at it in memory, double here now takes up 8 bytes because doubles take up that much more room. So it literally takes up this much space here. Okay. So double takes up 8 bytes and it takes up 4 bytes worth. So this thing, the ampersand, represents the memory address. There's a new type of variable now where we can actually store not a value, but we can actually store this, the address of a variable somewhere. And that's what pointers are for. A pointer lets you store the address of something. It lets you store one of these guys here instead of one of these guys, one of the values. Okay. So there's a new operator called it's the asterisk, the asterisk, which is actually called the indirect value or dereferencing operator. It looks like the multiplication operator. So let's talk about how this actually works. So I'm going to delete all this. So I'm going to call this, I'm going to create a variable called updates. And I'm going to create a pointer to updates, like that. This right here is your first introduction to a pointer. This is a way you can declare a variable to point to the address of something, but not to the actual value of something. How do we get the address of this again? Does anyone know what I just did? Remember? Ampersand is the address. So this is how I do pointer to updates. I can do that. So now I can point to the address of something. Why can't I just do this? I just have an integer. The address is a hexadecimal number, because the memory address of something in C++ is a special type of variable. It's not a number. It's not actually a number. Even though I'm showing it like a number here, like I'm showing it like 1000, it's actually something it treats it special. It's an address. It's not just a hexadecimal number. It's something unique. It's not an integer. It's not a string. It's not a bool. It's not a float. It's a special thing called a memory address. And that's why if you want to point to something that has a memory address on it, you need to use this pointer. That's the only way you can point to it. But why? Why do we care about pointers? Why is this something that's useful? So oftentimes, the reason why you want to point to the memory address of something is because sometimes you only want to have one of these in your game running at once. Remember, I said everything takes up memory, right? Everything takes up memory. Sometimes it takes up more memory than others. Like this variable here takes up 8 pieces of memory. But you know what? Like in Overwatch, some of these things take up way more than 8. Literally, some of these things take up megabytes of memory. Like we're talking like thousands and thousands of these rows. They take it up. And the reason why pointers are good is because it lets you point to one instance of it. It lets you point to the one place in memory, and so you don't have to copy it over and pay that memory cost over and over again. You don't want to spend a lot of cost in memory by duplicating the value over and over again. If you already have a value called 42 and you want to just use that value, you can. So a pointer lets you point to the memory because this pointer here takes up very little memory. Even if the thing it's pointing to is very large, this thing right here only takes up a little bit. So let's print out some of these numbers here. I'm going to print out that's going to print out the value of updates. So this is just a regular old cout. This is going to print out 6. And I'm going to print out the memory address of updates, which we just had here. I'm going to print out this. Okay. This is printing out the value, and this is printing out the memory address of it. You guys see that? 44FA50. This is exactly the same as if I typed in this. Okay? You guys see that? That's exactly the same. How do we print out the value of it? So we have the number here. Guess what? Even though you have a pointer to the memory address, if you have the memory address of something, you can actually get the value of it too. If you know where something lives, if all you know is the address of this, you can actually get the value that's stored there. And the way you get the value that's stored there is you use another operator, which lets you get the value of what's stored there. And the operator you use is by coincidence, is also the asterisk operator. Is also the asterisk operator. That is called the dereference updater. So, if I put an asterisk in front of a pointer, like this, that will print out the value at that address. This is different. This prints out the memory address that it's at. If I want the actual thing there, I do that. And that'll go and say, well, I don't actually want the address. I want the thing that it's pointing to. So let me show you what that means. I'm gonna do both. Okay. So here's the output of the program here. I'm going to print out 6, then I'm going to print out the address of where 6 lives, and then I'm going to print out 6 again because I'm going to get the address and I'm going to put a dereference operator in front of it to get the value. So what you'll see is there's 6, there's the memory address of 6, and that's the value at 6. Okay. All right, so let's do a little bit more. How else do I print the address here? I do ampersand updates. I'm going to group these up together. So these two are identical. These two lines are identical. Updates, and this gets me the value at that memory address, and this prints out the memory address of updates, and this prints out the memory address of updates. These two lines are identical. Pay careful attention to this. This is just the value, the number 6. Why does this give me the number 6? Think about why that actually works. Because this is just the memory address here, and then we put this asterisk in front of it, which then says, oh, don't give me the memory address, give me the actual value. And think about why this prints out the address of that value. Again, think back to the spreadsheet here. This is the, if I actually represent this with updates, if I actually call this thing int updates equals 6, and I run this, 4C F874. 4C F874. That's the memory address there. And this is going to be 4C5. And there's our memory addresses as they go forward. Okay, this is how the memory is working. So when I have a, I'm just going to do this. So that is where the memory is for 6. It is currently, this is the address of 6, and this is what's at 6. Okay. This is what's at 6. This is the value at 6. This is where 6 lives. This is also where 6 lives, because I have a pointer up here to update. Okay. How do I change? How would I add 1 to updates normally? I can do updates plus plus, or I can do updates equals updates plus 1, right? And I can see out. So here's the crazy part about pointers. And this might, hopefully it doesn't blow your mind, but hopefully it makes a lot more sense. So I'm just going to add 1 to updates, right? So you would expect updates to be 7, and it will be 7. Updates is now 7, right? But the crazy part is that I don't have to do this on the updates. I can grab my pointer to updates. Remember, this is the address of the updates. I can grab the value at that pointer. I can make it equal to the value at that pointer plus 1. This will change to be 7 now as well. I am changing a completely different variable, but it's actually changing this one here. Do you guys see how updates is 7? I didn't even touch updates here. I just touched the pointer to updates. I just made it 7. But updates itself changed. I don't have to make it. I could just make this thing 420. But look what I'm printing. I'm printing out the variable updates here. But I'm changing this guy here. So the dereference operator lets you get the value stored at this address. Okay? The value stored at this address was 6. When I do this operation here, what I'm actually doing on my spreadsheet is I'm going to go to this address. Oh, I say get the value, and I change this one to be 420. Okay? All right. Okay, let's go into the process of declaring pointers. So how do we actually declare pointers? Again, this is a pointer to an integer. You have to tell C++ what you want this thing to point to. It has to match the variable that you're working with. So if I had a variable called string, or maybe a float called updates, I need this. If it's a pointer, I want it to point to a float. This also has to be a float. These types have to match. And the way you say that is this is either a pointer to updates is a pointer to a float, or you have a float pointer called pointer to updates. Those are the two ways you call it. I usually say pointer to float or float pointer. Like typically it depends on what you're just saying. I will say like pointer to float or pointer to blah. This variable type here can be whatever variables are supported in C++ or any variables that you make. So for instance, if I had like a Pokemon, it's like Pikachu, and I wanted a pointer to a Pokemon, let me just get rid of the red squigglies. So here's my pointer to Pikachu. You can this works exactly the same way. Get the memory address of Pikachu and point to it. Okay. So if I go back, so here's my pointer to updates. This we know lives at this address, right? Lives at this address. Where does the variable for this lives? Because guess what? That's also a variable. What memory address does this live at? Because it has to live somewhere, and that is not actually known. Let's just let's find out where that thing lives. This is going to be 39FEC 39FE20. So we have, if I write these out, it's 39FEC FE2C. Doesn't know how to add. So that's where updates lives. This thing might live somewhere completely different. I'm just going to make up a thing here. And these pointers also take up, well, it depends on the operating system that you currently are working on. In this case here, they're actually going to take up 8 bytes of storage. This variable here. So now that I know this takes up 8 bytes, what's actually in here? This is where this variable lives. What's actually here? the value of it. What stuff is inside here? Remember, I said this thing stores memory addresses. So what's actually here?
All the memory address of
The memory address, which is what? That?
Yeah.
So it stores this. That's right. That's all. That's what is actually in there. It's crazy. This variable, which lives here, stores this memory address,
Yeah.
which has this value on it.
Inception.
Yeah, it's like Inception.
Weird.
It's weird. You have to think about it in terms of this. Imagine this. Whenever you think about pointers, imagine this in your head. Okay. This is going to imagine that you have memory addresses and stuff, because without thinking of both of those, you can't collect the two together. It's like you need both pieces of the puzzle to understand how pointers work. Yeah. So when I have this pointer variable, pointer to updates, and I just do a cout, I do cout pointer to updates, it's going to print out the stuff here. So it's going to print out this, right? That's why when I do a cout, it prints out that. Okay? How would I get it to print out this?
Take off the asterisk.
Well, when I'm printing it out right now, I don't have an asterisk on there. Look right here. This is what I'm doing for this line. I'm literally calling pointer to updates. That line right there is giving me this result. It's giving me the memory address of it's printing out the stuff inside.
Can you go back to that?
Add an ampersand in front of it. That will print out the memory address of where the pointer lives in memory.
So you print out the memory address, that's what the memory
And then
address.
if-
Yes, that's how it is. So I just want you guys to realize this variable is nothing different. It's just a variable like everything else. Even though it has a pointer, the only thing that's different about it is what stuff it stores inside. Okay, it doesn't store like a number or anything like that, or like Dark Souls 3 was an okay game. It doesn't store like a string or anything. All it does is stores a memory address. That's what pointers do. That's all pointers are. It's just they just store memory addresses. Okay, but that's the only thing they can store. And that's why there's special kind of operations, because if you want to get the value, that's what the nice part is. If all you know is this memory address right here, if that's all you know, you can work your way from here to here to here. And the way you do that, if you want to get the actual value, you put a number in front of it. There's a difference between printing out this and printing out this, which is the stuff that's pointing to. All right. Keep in mind, when you have a pointer variable like this, if you ever declare multiple pointer variables, like this, like a comma separated one, this is not a pointer. This is a pointer. If you want to do that, you have to put an asterisk in front of each one of these. This is why we don't do multiple variables on the same line, because it's confusing. If you're ever going to do that, just do this. Okay, multiple lines per variable. You can also initialize this on the same line. There's nothing stopping you from deleting this and doing this. Do that too. Okay, so here are some things to keep in mind that are risky when using pointers. It's just a memory address, right? So why can't I just do this? Why won't it let me do that? It's the memory address, right? This is a number. It looks like a memory address, but it's actually a number. The way you tell C++ that, hey, I actually want this to be a memory address, you have to do a very special piece of code to make this. This number right here is, even though it looks like a memory address, it's the same as 38. It's basically, you typed in this.
Yeah.
If you try to do this, you're trying to put the number 380,000 into the memory address here. You're trying to do this. Remember, you cannot store anything except for memory addresses in here. This is a number. You can't store a number in here.
So the C++ will read it as like if it's a number, but you're gonna type it as like the other way.
Right. Even though you're typing it like this, it's going to read it like this.
Gotcha.
And actually, what it reads it as ultimately is it reads it as this. So how do you get it to point to an address? You can actually have it point to a real address if you want to. And the way you do that by doing that. You don't ever want to do this. By the way, never do this. You never want to have a hard-coded memory address like this. This is just bad. This right here, this might have been the address of this variable when you ran it the last time, but guess what? That is not going to be the address every time. In fact, this number will never probably be the same again. This number might be, that might be the memory address for like OBS, or that might be the memory address for something else that Windows is using. Who knows what's in this location? It's really bad if you do stuff like this. Like, what is that pointing to?
That's like something on your operating system.
Yeah, maybe something really early that got allocated first, right? You don't know what that is. So this is why you don't do, you can do this, but this is not where you want to put that, okay?
You'll crash your whole.
Yeah, let me just put my kernel over here.
Yeah, and guess what? What happens if I do this? Okay, I picked a memory address 4. And I'm going to change what's there to be this number. I just blew away whatever was there. Who knows? I'm going to run this and I'm going to find out.
Write some shit.
It crashed. It was like, what are you trying to do? It's trying to say 4. You guys, can you see that has like question marks there? Here, let me show you the question marks.
Write that shit. This computers are worthless.
Crash.
Make them buy me
You guys see how it says question mark? Like, what? 4? What are you smoking?
What is that?
4? What do you mean 4?
Comprehend.
Right?
I cannot comprehend what you're trying to say.
Yeah.
What are you smoking on?
All right. Makes sense so far? Okay.
There's no way you need to mess with that file, trust me.
So that is how pointers to memory addresses work. Okay. Questions on this so far? Go ahead.
It was just that last part with the.
This
don't
part?
do that,
Like what?
don't-
Yeah, don't do this.
Yeah.
You wanna allocate it to stuff that's you know about ahead of time. This is safe because C++ will say, okay, I'm gonna put this somewhere, and you're saying, okay, wherever you put it, let me know where you put it so I can save it off.
Yeah.
Can you give us another example how pointers are useful?
Yes. So I will give you an example. So this right here is just a very, very basic. This is like 10% of what pointers do. So one of the best ways you can do this is when you're passing arguments to functions, you can use pointers. And that way, if you have a variable like updates here, if I have a void function, like let's say I have a void function, I don't know, what should we call this? Change updates. Change. This is a much later example, but this is a good one. Normally, it takes an integer of a value, right? And if I just say value equals 42, and I call this function change value 6, or I'm sorry, not 6, updates, and I do cout updates, what will that actually print out? What will that cout statement print out? Does anyone know? I'm sorry. Let me. So there's my function. I take a value. I'm saying value equal to 42, and then print out. It'll print out 6 because you're basically passing in 6 here. This is going to change to be 6. It's going to copy 6. It's going to set value equal to 42. Come back. This number is still going to be 40. This number is still going to be 6. Like if I run this, let me show you how this happens. Updates is currently 6, right? I'm going to go into this function. Value is currently 6, right? I change value to be 42. I come back. Updates is still 6. Because you know why? Because when you called this, you didn't pass in the address. You actually just passed in the value. You literally said, okay, just take this guy and work with it. Just take that number and work with it. You're not passing in this. And the reason why it's important is because if you want to, you can actually use a special parameter to pass in the memory address of this thing. And it's called passing by reference, which allow you to change this value here. I kind of don't want to show it to you because this is kind of more, this is actually chapter like 9 and 10. We're not going to do this quite yet. I really want to get through the pointer stuff first. Let me answer your question a little better with the next pointer example, because I think the existing stuff, if you wanted to, you could look up pass by reference, but you use the ampersand operator here, and that will let you pass it by reference. All right, so let's do another example of pointers, just to get you guys a little bit aware of why this is useful. And remember, pointers are also used for cases where you don't know how much memory you need. So a pointer is the only way you can actually allocate, like, let's say I need 3 gigs of your memory right now. I didn't need it like a second ago, but I need it right now because you just opened the door to your Skyrim house and I need to basically load in all your crap that you threw in there. Pointers will let you basically allocate memory. And the way that you allocate memory is by using the next operator, which I'm going to teach you, which is the new operator. Something called new. So there's something called named memory and unnamed memory. So named memory is the stuff that we've been doing so far called like updates. This memory is something that C++ knows way ahead of time. Right when I build it, it knows, oh, I'm going to allocate space for this right now. Sometimes, though, you want to allocate unnamed memory. This is basically allocating memory from someplace that C++ didn't know about yet. And pointers are the only way to do that. So let's do that right now. So I'm going to create a pointer called pointer to integer. And I'm going to get memory back that C++ doesn't know about yet. So when I run this right now and not have it do anything, C++ literally was like, well, I guess you didn't need to do anything with this pointer. I'm just gonna like bail. I'm not gonna give you anything for it. But you can say like, oh, hold up, C++. This right here is letting you allocate. You're basically asking for a chunk of memory like this. You're asking for a chunk of memory from somewhere that Windows has. And you're asking for a chunk of memory that C++ didn't know about until this time that you just asked for. So when you call new and pass in the type of your pointer here, C++ is going to be like, shit, hold up, hang on. I need to get you memory. Just wait right here. It runs off, finds a piece of memory somewhere that's available in RAM, and comes back and it's like, okay, here. I don't know about this. Here's a piece of memory you can use right now, and go ahead and do whatever you want with it. So you're basically asking for a place to put an integer variable, and this is what this thing does. Because in order to actually put an integer variable, you need to have a place to store it. So let's do another example here.
Does it mean the memory size increase or?
It does. Every time you call this, memory goes up. In fact, maybe I can show you guys a good example of this. If I just make an infinite loop here, this might be scary. We'll see how bad this goes. I'm going to run this, and I'm going to have you guys watch this. Can you guys see my memory usage going up here? You guys see how it's at like 1.7 gigs now? Can you guys see how it's actually going up and up?
Yeah.
You guys see that?
Should really break it. Just break the computer. Just make it buy a new one.
Oh, I ran out of memory.
Hate these computers.
You know why I ran out of memory? Because I'm running a 64. Here, let's do 64-bit.
Yeah, there it is.
And let's do something a little bigger. Let's do a double.
Say they put 6 more gigs in this.
I'm just going to show you guys because this is why this is important. Here's my project right here. Here's my memory. Going up a lot. My computer may actually crash.
Yes, make it crash.
Perfect.
It is.
What you should do, you should make it crash.
Oh, I don't have. If I crash, I won't have the video, by the way.
Don't crash.
It's on the name of almost there.
Okay, I'm going to stop it because it's already almost at 10 gigs.
I like how it says kernel not loaded.
So
Like I said,
that's what the new thing does. It goes and gets you memory from somewhere. And if you're running a 64-bit operating system and running a 64-bit game or something, there's actually the limit to it is 2 to the 64 bytes. So if I just do that too quick, if I just calculate what 2 to the 64, that's how many bytes. So how many megabytes is that? That's kilobytes, megabytes, gigabytes. That's how many gigabytes of memory it has. Terabytes, petabytes. 16 petabytes of memory. That's how much memory you could, in theory, take up. So the only limit in this case is how much hard drive space I actually have. Because when it starts running out of RAM, what it actually ends up doing is start taking memory from your hard drive. It creates a file on your hard drive and starts taking up space from there.
Yep, starts using virtual RAM.
Yeah, it starts using what's called your page file.
Yep.
And so if it runs out of RAM, it's like, shit, well, I need more. He's asking for more. When's he going to stop? Well, he'll never stop. But the reason why this is good, you can't do this. You can't just allocate like 10 gigs of memory in your program like up front, because you don't want to do that. You don't necessarily want to do that until you know you have to, right? If you're running like a game, you don't want to always take up 10 gigs of RAM at the very beginning. You only really want to use as much memory as you need, right? You don't want to take up any more, which is why pointers are important, because they let you get, and you can return that memory back when you're done with it, which is the last piece of important bit. I'm going to show you guys how to return that memory back in just a second. So let's just finish this example here. So this got me a chunk of memory that I can store. So what it actually got me back is a chunk of memory for this. It basically got me back a piece of memory that looks like this, right here. There's no variable or anything like that. This is literally just, hey, it's blank. Nothing's pointing to it right now except for you. There's no variable or anything like that. Just here's 4 bytes of memory, and here's where you can put your stuff. So now that I have this, I have my stuff. And so what I can do is I can say pointer to integer. I can get, remember, this is going to store the address to my stuff that I got. And I can set this equal to 420 now.
4 days.
I'm just using 420 because it's the first number that came into my head. All right. So this will now print out 420. But hold up for a second. Let me show you what happens when you don't do things correctly. So there's 420, right? What would happen if I didn't do this?
I'm assuming I get jumped.
So what actually happens if I don't do that? So remember, my pointer has to point to something, right? So I'm just going to just delete that. This is what my pointer variable looks like right now. I have a pointer to an integer. And I literally, it doesn't have any stuff inside of it. In fact, this stuff, if you haven't assigned anything, is garbage. So it's like CC, DC, blah, blah. It's like, it's garbage. You don't actually know. It's whatever was there the last time you used that memory. Okay? And it might be these numbers, might be just completely garbage values here. Okay? So what happens when I try to get the value at this address?
It gets you over there last time.
Well, what's at CC? Remember when we tried to get 4?
There's no address.
There's nothing there, right? It's garbage. Yep. So when I try to do this, it's like, okay, let me go ahead and put whatever's here and make that equal to 420. Well, this is a problem because I don't have anything there yet. So what'll happen typically is it's undefined. What typically happens is that there's a crash. It's not even going to let me compile it. Let's see if I can get this thing to. I'm just going to let this equal to int. I'm just going to do my example CC. So what happens here? Again, it crashed. Because I didn't ask, I needed a piece of memory. I can't just use whatever's there. So this is why when you use new, like this, now you set this thing equal to a chunk of, now this whole thing is nice and clean, it's been deleted. You'll get a piece of memory here that's valid, I don't know, like 4.2. You get a nice chunk of memory here, and all these things are, it's free, it has nothing inside of it. And now I can set whatever's in here, this thing gives back this memory address, okay? So now pointer points to this chunk of memory here that I got back when I called new. And now when I dereference it, now I can set this equal to 420 until everything's good and happy. All right? So let's go back. This will be the last thing. I'm going to have you guys read a little bit too. Remember that example that I showed of running out of memory? If I just do this, okay, and I just run this infinitely, I'm going to run out of memory and probably crash my computer. Maybe, we'll see. There might be safeguards in place, so the page file eventually, it might not crash, it might just slow it down really heavily. But I'm getting memory. If you don't want the memory anymore or you don't need it anymore, you can give it back to the operating system. If you call delete, the new and delete are like good friends. These two guys kind of always have to hang out together. Anytime you allocate memory, at some point, you should be like, I don't need that memory anymore. Like the Skyrim example of opening your house and needing all this memory to store all the shit that you collected. When you leave your house, you don't need that memory anymore. So what you should be doing, you should be deleting all that memory that you got. So watch what happens now to my memory when I run this. So look at my project here. You guys see how much memory it's taking up?
Not a lot.
It's the same, because I'm getting memory and then I'm putting it back. If I didn't delete it, if I didn't have this line right here and just run it, there it goes up again.
Is there such a thing as recycling memory?
You mean reusing the memory?
Yeah.
So that's what so yes, there's two things. One, the operating system will sometimes give you back memory that's been used previously. In Overwatch and in very commonly in games, what you do is up front, you'll allocate what's called a memory pool. You'll say, hey, give me, I don't know, 100 megabytes. Just give me a huge chunk of 100 megabytes. And you will, within 100 megabytes, you will grab and return things as you need to. So you will reuse things in the 100 megabyte chunk. That's what's called a memory pool. There's a whole big discussion. One of the game engine architecture books that I recommend to read has all about how to do memory pools and object management. But for most games, this is fine. Like for your games, new and delete is fine. All right?
So would that kind of be like the heap, or
This is coming out of the heap.
okay.
So there's different. The heap is basically unnamed memory. It's memory that you get back when you call new. It's all any memory, anytime you call new, all that memory comes out of the heap.
Okay.
Anything that you declare like this is coming out of the stack. Just keep that in mind. Okay. That's not really critical. It's basically between named and unnamed memory. All right. So I want you guys for homework. Other questions? Does it kind of make sense a little bit? Hopefully you guys don't forget all of this next week because I'm going to jump into more pointer usage. This stuff is really easy to forget about. Remember, think about it in context of this spreadsheet. Like kind of picture this spreadsheet in your head when you're thinking about pointers. It'll help you understand it a little bit more. All right? So the homework, I want you to do, you're going to have to read chapter 4. So basically read the section on pointers because we just went over that. And then I want you to do exercises 7, 8, and 9 in chapter 4. And all these multiple choice questions. Okay? These are basically exactly what we just went over in class. This question number 12 here, this is something we didn't go over yet. This is from the book. So this is basically out of page... Sorry. This is page 156. This last question is you have to read page 156 to go over. So try your best to do that, and we'll review this homework. I kind of want you guys to read and see if you can figure out the answer to this, because it's kind of trickier. Like don't look at this until you've done all the rest, though. All right. That's it. Thanks, guys. See you guys next week, class. I'll upload this to YouTube.